Hello everybody and welcome to my YouTube channel. Today we'll be looking at how to solve the problem. Find the number of 5-digit positive integers such that the digits are non-increasing from left to right. Okay, so first of all, non-increasing means it's either decreasing or equal to. So basically we just want to find the total number of orderings A, B, C, D, E, satisfying the conditions that 9 is greater than or equal to A, B, C, D, E, which is greater than or equal to 0, since all the digits are greater than or equal to 0. Okay, so if we wanted to count the number of orderings directly, we would have to do casework based on whether A, B, C, D, E were distinct or not. If A, B, C, D, E was distinct, then we'd be able to count it easily using combinations. But if A, B, C, D, E was not distinct, then we would have to do subcases based on which digits are not distinct, and if they're not distinct, how many times and where they appear. In general, it's just troublesome. So it would be much more convenient if we could find a way to solve the problem of these 5 digits not being distinct. Actually, there is a way to solve the problem, and I'll demonstrate. Say, for example, you have an ordered pair where the digits are not distinct. Say 7, 6, 5, 4, 4. Okay, say that I added 4 here, I added 3 here, I added 2 here, I added 1 here, and then I added 0 here. Then I could transform this old ordering into the new ordering 11, 9, 7, 5, 4. Okay, originally these two 4s were not distinct, but now they're distinct because one turned into a 5 and the other is still a 4. Does this hold for any A, B, C, D, E? Well, let's see. So A, B, C, D, E is transformed into A plus 4, B plus 3, C plus 2, D plus 1, and then E. Okay, so are these 5 numbers all distinct? Well, let's see. We know that E is less than or equal to D, so the greatest E can be is equal to D. That means E is always less than D plus 1. Well, E will never be equal to D plus 1, so they're distinct. Similarly, D is less than or equal to C, so D is less than C plus 1. This implies D plus 1 is less than C plus 2, so D plus 1 and C plus 2 are also distinct. The same holds for C plus 2 and B plus 3. They're distinct, and so are B plus 3 and A plus 4. The 5 numbers here are all distinct. So yeah, looks like this transformation solves the problem of the original digits being undistinct. Alright, so now we solved the problem of the digits being distinct. But I would like you to note that the transformation we used to turn our digits into distinct numbers is a bijection, because from this old ordering, I added the corresponding increments to turn it into the new ordering. And from the new ordering, I can subtract the corresponding increments and turn it back to the old ordering. This tells us that the transformation I did was a bijection. So basically it means that the number of old orderings equals the number of new orderings. So originally we wanted to count the number of old orderings, and it was hard because the digits weren't distinct. Now we just need to count the number of new orderings, and it's easy because the numbers are distinct. Alright, so the lower bound for the new orderings is 0 because E, which is the least of them, is always greater than or equal to 0. The upper bound is 13 because A plus 4 is the greatest, and A is always less than or equal to 4, so A plus 4 is always less than or equal to 13. Alright, so the number of new orderings is basically the number of ways to take 5 distinct elements from a set of 14 integers, which is 0, 1, 2, all the way to 13. Yeah, the number of ways to take 5 integers from the set of 14 integers would be C, 5 out of 14. But remember that the leading digit, which is A, is not equal to 0. Well, if A was equal to 0, then we'd end up with the ordering 0, 0, 0, 0, 0. This would give us the new ordering of 4, 3, 2, 1, 0. And we do not want to include it because 0, 0, 0, 0, 0 just represents 0, which is not a 5-digit positive integer at all, so it's not going to satisfy the conditions of the problem. We do not want to take a 4, 3, 2, 1, and a 0 out of this set, but we did, because C5 out of 14 includes all the possible ways to take 5 distinct integers out of this set, and obviously 4, 3, 2, 1, 0 is one of them. This means that we mistakenly included a number that should not have been included, so we're going to have to subtract 1 to recompensate. This renders us with the final answer of 2002 minus 1, which is 2001. All right, 2001. That's our final answer. Well, of course, this isn't the only way to do this problem, because there's another more straightforward way that you could have done it. Basically, you let A range from 1 to 9 because A is non-zero, and then once A is given, B can range from 0 to A, and then once B is given, C can range from 0 to B, and then D will range from 0 to C, and then E will range from 0 to D, and then we're going to sum 1 since we only want to count each 5-digit positive integer once. Alright, yes, this expression would give us our correct answer if you are able to calculate it. The only problem with this method is that the expression is not easy to calculate by hand, since these 4 sigmas here are going to sum into a 4th degree polynomial, and then we're going to end up having to sum a 4th degree polynomial by hand, which is not easy at all. Okay, another way that you could have done this problem is, well, you could have made the observation that each 5-digit positive integer has a unique digit combination. Well, what I mean is that, for example, our number 76544, it composes of the digits 2 4s, 1 5, 1 6, and 1 7. And if you were to build a 5-digit positive integer satisfying the conditions from 2 4s, 1 5, 1 6, 1 7, the only number that you would get is the number 76544. Let me draw that out. From this number has a unique digit combination of 7 6 5 4 4. And then from this digit combination, I can only build one number that satisfies the conditions. That's one-to-one correspondence. Tells me that the number of 5-digit positive integers satisfying the conditions is equal to the number of possible digit combinations. Because for every digit combination, I'll get a 5-digit positive integer, and for every 5-digit positive integer, I'll get a digit combination. So it only remains to count the total number of digit combinations, and a little hint for that is that you have to know that the total number of digit combinations is basically the total number of solutions to the equation x0 plus x1 plus ... plus x9. I'm lagging a little, equals 5. Okay, where x0 represents the number of zeros you're going to use, 1 is going to represent the number of ones you're going to use, 9 is going to represent the number of nines you're going to use, and of course each of the 10 variables here takes an integer value and is greater than or equal to 10. There's a very neat way to calculate the total number of solutions. It's known as the stars and bars method. Basically, it builds a one-to-one correspondence between a permutation of 5 stars and 9 bars with the solutions of this equation. So basically, the number of solutions to this equation just equals the number of permutations of 5 stars and 9 bars. And then that's C, 5 out of 14. And if you account for the condition that A is non-zero, or the leading digit is non-zero, then you're going to have to subtract 1. and then you'll get the same answer as up here, which is 2001. Okay, so that's another way that you could have done this method. Done this problem. Well, different people have different preferences, and which method you choose is totally up to you, because you might notice things differently. Like you could have saw that uh, you could have noticed this trick to solve the problem of digits not being distinct first, and then you would have used this method, or you could have noticed that the 5-digit positive integers had a one-to-one correspondence with their digit combinations, and then you might have ended up using this method. So yeah, it depends. Okay, so I guess this concludes my video. Goodbye.